This project is to find the relation between atomic polarizability, which is calculated, and the numbers of various kinds of atoms using the QM9 subset Mordred_DF.CSV. This data set only has 4 kinds of atoms: the number of carbon, number of hydrogen, number of oxygen, number of nitrogen are the features selected. The QM9 data set has about 130,000 molecules. The Mordred subset has 2,500. Correlation and mini-sum graphical outputs seem reasonable. Multiple linear regression shows good agreement with predicted and actual atomic polarizability in dataset. Atomic polarizability, apole, is defined by the equation dipole is equal to polarizability multiplied by electric field. Apole is 1/3 the trace of the tensor alpha, or the average of the diagonal elements. Results show that there is a multilinear relationship between carbon, hydrogen, oxygen, and nitrogen numbers and the polarizability in the Mordred dataset. We begin by installing the mini-sum program and some libraries. And we check to see that we have data. Or we read it in with the read CSV Mordred_DF.CSV, and then we check to see whether we do have data. We have the data set has 2,500 rows and 1,845 columns. We picked 5 features from the data set as the training data for the SOM. The SOM is abbreviation for self-organizing map, or Cahonan maps, is a type of artificial neural network. The meaning of the descriptors, the columns in the data set, can be found in this link. We normalize the features, getting ready to use them in making correlation matrix. And we have a subset of the data where we have the 5 columns, and that's 4 of them are the features, and the apole is the target. And we normalize them by subtracting the mean and dividing by the standard deviation. Now let's look at the correlation, the Pearson correlation matrix. We import the Seaborn, and we find the heat map of the correlation, and we show it in this figure. There are 5 columns and 5 rows. The diagonals are always 1 because the features are correlated to themselves. The carbon, hydrogen, and apole have some correlation. The correlation matrix shows values of 1 being correlated and -1 is not correlated, with variations in between. Let's look at the self-organizing matrix, self-organizing map. It will produce a 2-dimensional representation of the 5-dimensional subset. Let's train the SOM and define a mini-sum object of 50 by 50. And we initialize the weights with PCA, and we train the sum with specified iterations of 5,000. And we get the weights of each node and display the heat maps of the 5 features. It's the oxygen, the nitrogen, and the A-pole. We can compare the heat maps better when they are side by side. So we make a figure with the side by side, and you can see that they really are different. The hydrogen and the carbon are similar, but they're not exactly the same. The feature correlation showed only the carbon and the hydrogen and the A-pole more correlated. The heat maps from mini-sums show all are different and so not correlated. The features are independent, and so we'll use 4 features in regression to predict the 5th feature, the target A-pole. We will try Susi's SOM regressor from GitHub, from Felix Reese, to see what results can be had and compare this to multilinear regression. So let's install SUSI. It's installing, and we do a train test split, and we have the libraries for installing the train test split and the other things, and we have X as the subset of the with the 4 features, and Y is the target. And we split the data set, and I'm using the recommended values from the example on the website of the SUSI sum. And the test size is 0.5, so it's 50-50 test and train is what he used. And we make an instance, a susum, and these are the defaults and the recommended for regression. And we normalize and form X train and X test, and then we fit and we predict, and we plot Y test and Y predicted, and it's looks somewhat of a straight line, but a little fatter. And the R squared score, if a train is 94.3 and the test is 94.1%, when the train and the test are close to each other, we say that there's less overfitting chance. So the SOM regressor reports R squared score of 0.94 with standard scaling and 0.98 without standard scaling, using the default parameters. SUSI cannot give the coefficients or interceptor fit, since SUSI is a nonlinear regressor and classifier. Let us try to optimize the hyperparameters with optimization. So we create an instance of the SOM regressor, and we've changed the grid size of 50, we've increased to 50 by 50. And now we use this wonderful program And this is our dictionary of what we're optimizing. The randomized search CV. This randomized search will do a cross-validation of 5 times in the search. And we train and fit. I mean, we fit the training data. and it comes up with some suggestions for optimization, and we put that in, and we make another instance of the SOM regressor and put in what the optimizer said was the best, and we make an instance of best SOM fit, X train, Y train, and we predict, and we plot. And yes, that looks more straight, the line. And the R-squared values for the test is 0.987. The best SOM regressor, simply optimized by random search CV, gave an R-squared score of 0.987. It's pretty good for a nonlinear regressor. Now let's try the simple multilinear regression. First we split the data into train and test, and then we normalize. So here's our X and Y, and we import the train test split, and here we split our test size is 0.2. So the training data is 80% of the data, and the test is 20%. Now we do the standard scalar to normalize things, and we're importing some we're importing some libraries. Might have already imported them. And then we form the instance of the regression. We do the linear model. We import linear model, and regr0 is our instance of the linear model, and we fit, and we train, and we predict the testing data and compare the plot, and it's a very straight line. And here's the intercept and coefficients. So this means that the A-pole is predicted to be approximately, by the equation, 17.7 plus 0.4 times the number of carbons plus 1.6 times the number of hydrogens minus 0.4 times the number of oxygens minus 0.1 times the number of nitrogen atoms. And let's evaluate the error. The R2 comes out to be 1.0, and the mean square error is 1 times 10 to the minus 29th. It's very close to 0. This simple multilinear regression outperforms susi's SOM regressor. The dataset subset of QM9 only has atoms carbon, hydrogen, oxygen, and nitrogen. The number of carbon, hydrogen, oxygen, and nitrogen atoms is sufficient to predict the atomic polarizability. R squared, R2 equals 1, and mean squared error, MSE, almost 0, is as good as you can get. Nothing could be better. Thank you.